All right, welcome. Today we're going to build your personal toolkit for the world of electronics. We're talking about how to look at these sometimes crazy looking circuits, understand them, and yeah, basically tame them.
Okay, let's dive right in. You look at a circuit diagram like this, and it can feel like you're just staring at a plate of spaghetti, right? Super overwhelming. But what if I told you there are these really elegant shortcuts, ways to find exactly what you need, like say, the voltage right at that one spot, without the massive headache?
So that's the plan. We're going to build this toolkit together, piece by piece. First, we'll cover how to combine resistors. Then we'll get into some awesome shortcuts for voltage and current. After that, we'll touch on measurement and some advanced tricks, and we'll wrap it all up by revealing the secret behind a piece of tech you have definitely used.
Okay, first up, Section 1. We're going to master the most fundamental technique of all, combining resistors. Seriously, this is the bedrock for simplifying pretty much any circuit you're ever going to see.
So check this out. It really all boils down to two core situations. You've got resistors in series, or you've got them in parallel. When they're in series, they have to share the exact same current. It has nowhere else to go. But in parallel, they share the same voltage. And that one little difference has this huge impact. In series, your total resistance gets bigger, but in parallel, it actually gets smaller.
And for resistors in series, the math is, well, it's about as friendly as it gets. The equivalent resistance, basically what the circuit sees as one single resistor, is just the sum of all the individual ones. You just add them up. Super simple.
Now with parallel, it's a little different. Here, we're summing the reciprocals, the 1/over values. The really important thing to remember here is that your final answer, your equivalent resistance, is always going to be smaller than your smallest individual resistor. It's kind of like opening up more lanes on a highway. The overall traffic just flows way more easily.
And hey, here's a fantastic pro tip you will use all the time. When you've only got two resistors in parallel, you can totally skip the whole reciprocal thing and just use this, the product over sum formula. You just multiply their values on the top, add them on the bottom, bam! It's a huge time saver, for sure.
Okay, so let's keep building on this. Now that we know how to simplify these resistor networks, let's add some really powerful shortcuts to our toolkit. These are going to let us find specific voltages and currents without having to solve the whole entire puzzle.
Okay, the voltage divider rule. This thing is an absolutely brilliant trick for series circuits. It lets you find the voltage across any single resistor in that chain without ever having to calculate the current. It's like a direct path to the answer. All you need to know is the ratio of your target resistor to the total resistance.
So here's the key takeaway, right? The voltage drop is directly proportional to the resistance. You can think of the total voltage like a pizza. The bigger the resistor, the bigger its slice of that pizza. And this simple formula, it just lets you calculate the size of any slice you want.
All right, so if the voltage divider is the go-to for series circuits, what about parallel circuits? Well, for that, we have the current divider, and it comes with this really fascinating, kind of counterintuitive twist.
You're going to want to pay close attention here. To find the current flowing through, say, resistor 1, the formula actually uses the value of resistor 2 on top. So why does it do that? Well, you have to remember that current is kind of lazy. It always prefers the path of least resistance. So what you have here is an inverse relationship. The more resistance one path has, the less current it gets.
Okay, our toolkit is getting pretty advanced at this point. So let's add a couple of final pieces. We'll look at the tools for actually measuring these things in the real world, and then a special technique for those really tricky circuits that don't follow the simple rules.
This is a great comparison because it really shows the key differences between our two main measurement tools. To measure current with an ammeter, you literally have to break the circuit and stick the meter in series. For it to not mess up your measurement, it needs to have basically zero resistance. But a voltmeter, you just connect it in parallel across whatever you want to measure, and it needs to have infinite resistance so it doesn't steal any current. They are complete opposites in how they work.
So what happens when you run into a circuit that you just can't simplify with series and parallel rules? Well, that's when you bring out the specialty tools. You've got things like the Wheatstone bridge, which is this really clever setup for precisely measuring an unknown resistance, or the delta to Y transformation, which is basically a math trick to reshape complex circuits so you can simplify them. We're not going to dive deep on these, but they're what you'd learn next to expand your toolkit even further.
Okay, so after all this theory, why does any of this matter? Well, this is the payoff. We're going to take one of the most powerful tools from our kit, that voltage divider, and use it to reveal the secret behind a technology that I guarantee you have used.
Yeah, if you've ever used an older ATM or one of those early car navigation systems, or maybe a classic Nintendo DS, you have personally used this principle. Those old-school resistive touchscreens, they're a perfect real-world example of the simple circuit theory we've just been talking about.
So here's the breakdown of how it actually works. The screen is basically two flexible sheets of plastic, and each one is coated with a resistive material. And they're separated by this tiny, tiny gap. Now, when you press down with your finger or a stylus, you make those two sheets touch at one specific point. That touch creates a connection, and it physically divides the total resistance of the sheets right where you pressed.
And what's the magic that makes it all work? What's the secret sauce? It is our good friend, the voltage divider rule. The device measures the voltage at that exact touch point. And since the voltage is proportional to the resistance, and the resistance is proportional to where your finger is, the voltage it measures tells the system the exact X and Y coordinates of your touch. It's happening in real time. So cool.
So now you've got this toolkit, and I want you to start looking around. You know, from the dimmer switch on your wall that changes the brightness, to the volume knob on an old stereo. You can now start to see these simple but really clever resistive circuits hiding in plain sight all around you. What else can you find?